Hi, my name is Prakash Murali, and today I'm going to be talking about how to use computer architecture techniques to design better quantum computers. So, quantum computers are composed of qubits. These are the basic building blocks of the system, and the operations we can do on these qubits are called gates. So, currently we have 5 to 54 qubit systems which are operational, and the gates that we can apply on these on qubits in these systems are noisy. So, these systems are called noisy intermediate scale quantum systems. Now, in spite of their limitations, the Q systems actually have very powerful computational capabilities. So even with about 50 plus qubits, we have access to a very large state space. So Google recently showed that on a 54 qubit quantum chip, we can run a computation that is impossible on any classical hardware. Now, on the other hand, we have these large quantum applications like source factoring, which require thousands or millions of qubits for any advantage. So there is this huge gap between the resource requirements of the algorithms that we want to run and the hardware that we can build. So we need new algorithms, compilers, and architecture for efficiently using these devices. So in this talk, we're going to be focusing on a particular technology called trapped ion quantum computing. So in this technology, the qubits are built out of ions. So ions like calcium or ytterbium ions are the qubits. The energy states of these ions are used to represent 0 and 1 states for the qubit. And in a trapped ion computer, the qubits are trapped in an electromagnetic field. So this figure here shows an example of a real trap from Sandia. So this qubit region holds a linear chain of ions. So trapped ion systems have several advantages over other competing technologies like superconducting qubits. And I won't have time to go into all of the differences, but one of the key advantages is that trapped ion systems have full connectivity. So what this means is that we can run gates between any pair of ions within any pair of ions as long as they're in the same trap. In contrast, if you look at superconducting systems like IBM systems, the connectivity topology is quite restricted. For example, they tend to have very planar connectivity graphs. So now that we have systems with 5 to 10 qubits, 5 to 10 trapped ion qubits, to progress to the next major milestone of 50 to 100 qubits, we need to scale up our devices. But we have a fundamental bottleneck here, which is that all the current trapped ion systems are based on this architecture where all the ions are housed in the same trap. So it's a single trap architecture, and this architecture has some fundamental scaling bottlenecks. So these difficulties with the single trap architecture were recognized very early on. So in fact, in 2002, there was a proposal called QCCD to help scale up trapped ion technology. So what QCCD does is to separate out the ions into a set of small traps, and these traps are interconnected by something called shuttling. So what shuttling means is that when I want to run a gate between two ions which are in two different traps, I can physically move the ion from one trap to the other and then perform the gate. So the first QCCD system was actually recently built. So Honeywell built a 4 qubit system recently to demonstrate the working of this architecture. And now there are several industry and academic efforts looking at how to scale this up to the 50 plus qubit range. So the key question that our work addresses is how should we architect the next major milestone of 50 to 100 qubit QCCD systems? So what makes this difficult? There are a wide range of design choices that need to be made by a hardware designer. We need to pick the right trap capacity. We need to pick a good device topology, and we need to pick the methods required for implementing the gates and for shuttling. And currently, there's very little or no guidance available to designers on the performance and reliability of these trade-offs. There are models known for these aspects individually, but at the level of an application, it's very hard to reason about the performance or reliability. And we have very high gate error rates in the NSQ era, and our hardware should support an evolving mix of QC applications. So what this means is that if we simply design our hardware in isolation without looking at the software capabilities or the requirements of our algorithms, we are likely to face very severe reliability and performance issues in our systems. So in terms of prior works, there have actually been several recent works on designing quantum systems, but most of these tend to focus on superconducting systems, and there's been relatively less attention on trapped ion systems. And if you look at trapped ion work, there are several proposals to design very large systems with millions of qubits, and there have also been architectural evaluations of current systems. But these studies are not directly applicable to QCCD devices of the range that we are looking at. So our work brings computer architecture techniques to design reliable QCCD systems in the 50 to 100 qubit range. So to do this, we built a design tool flow which has a compiler and a simulator. And we identify and we evaluate a wide range of microarchitectural and architectural choices. And from this evaluation, we make recommendations for trap sizing, for device topology, and for operational implementations. So one of the key results is that if we tune our architecture well, we can potentially improve the reliability by about 3 orders of magnitude. And if we tune our microarchitecture choices well, we can further improve the reliability by 1 more order of magnitude. And in the NISQ era, where we have high operational error rates and low reliability, these kind of reliability improvements are likely to make the difference between failed application runs and successful runs. So now let's look at some of the design trade-offs in these systems. So the first design factor is trap sizing. That is, how many ions should I put in each trap? So let's first look at the advantages of having high capacity. So in these systems, it is known that shuttling is a time-consuming and error-prone operation. So shuttling heats up the ion chains, and it also increases the vibrations in these ion chains, which makes the gates harder to perform and makes the gates unreliable. So if you have high trap capacity, we can reduce the amount of shuttling required, and this can improve the application's performance as well as fidelity. But what are the drawbacks of having higher capacity? One of the main drawbacks is that as the ion chain grows in size, there is a lesser interaction strength between distant ions. So this can make our 2-qubit gates slower and also less reliable. Another difficulty is that the most common way of implementing 2-qubit gates uses lasers. So if I want to run gates on 2 ions, we pulse these 2 ions using laser controllers. And if when we have a large number of ions in the same trap, this reduces the spacing between the ions, which makes it difficult to selectively target qubits using lasers. And there are also some crosstalk issues at large ion count. So overall, if we have high capacity, it is beneficial because it reduces communication, but it also has these different drawbacks. Now, looking at topology, there are similar trade-offs here. So when we want to perform an ion shuttling operation, there are several operations required to accomplish this. We need to split an ion from the trap where it resides. We need to move it along a series of paths. We need to turn if we encounter junctions, and we need to merge it at the destination trap. Now, it's known from real experiments that these splits and mergers are actually less reliable compared to moves and turns. And it's also known that 3-way and 4-way turns are actually harder than simple straight moves. So if you want to compare a linear and a grid topology, so by the way, this linear topology with 6 traps is actually Honeywell's current topology. So if we have a linear topology like this, when we want to move an ion from, let's say, the first trap to the 4th trap, this ion has to pass through some intermediate traps. And at these intermediate traps, we need to split and merge. So there are more splits and merges, but there are no turns to make. In contrast with the grid topology, there are less splits and merges that we need to make, but the turns are harder. So there are different trade-offs for these different topologies based on what applications we're going to be running on them. Finally, looking at microarchitecture, there are 2 choices that we need to make. 1, how to implement our gates, and 2, how to implement shuttling. So in terms of gates, all the 2-qubit gates that we want to run in the system are basically the same logical operation, but there are different ways of implementing this operation in hardware by manipulating different laser parameters. So we consider the most common ways of implementing these gates, which includes frequency modulation, amplitude, and phase modulation. So depending on what method we pick, there are different trade-offs. For example, frequency modulated gates have execution durations which depend only on the trap capacity and not on how far away the ions are within the same trap. While in amplitude modulation, if 2 ions are close to each other, the gates are fast, and if they're at the far ends of the same chain, the gate is actually slow. And these differences are not just in terms of durations, they also directly translate to differences in fidelity. Now, similarly, there are also some trade-offs with respect to how to implement shuttling. So what we need to implement shuttling, one of the choices we need to make is that we need a method for reordering the ions in a chain. So for example, if I want to move this yellow ion from here to here, I need to first bring the yellow ion to the right end of this first chain before I can split it off from this chain. So there are two options for how to implement this, and you can find more details about these two options and their trade-offs in the paper. So overall, our work looks at three sets of design questions. First, in terms of trap sizing, we look at for QCCD systems with 50 to 100 qubits, what trap sizes really work well, especially considering NISQ applications, and to what extent do the application characteristics like 2-qubit gate patterns inform our sizing considerations. Similarly, for shuttling topology, we look at what topologies are going to work well for these systems and how much does topology really affect the application's reliability. And in terms of microarchitecture, we study the best methods of implementing 2-qubit gates and chain reordering. So to evaluate these choices, we built a design tool flow, which consists of this compiler and a simulator and a set of performance and noise models. So a compiler takes a candidate devices architecture and a set of benchmark programs and compiles these programs for execution onto this device. The simulator takes these executables, it takes these noise and performance models, and it estimates what the application's reliability, runtime, and resource requirements are. And it also estimates the device's behavior in terms of noise rates and heating rates and so on. So in terms of compilation, current compilers don't really support QCCD systems. So we had to build a configurable compiler for this class of systems. The architectural attributes like trap sizes are actually input to this compiler along with the program's intermediate representation. And the compiler maps the program qubits down to the hardware qubits in the system, and it orchestrates the ion shuttles. So the key objective that the compiler tries to achieve is to reduce the shuttling requirements because shuttling is expensive and leads to poor gate fidelity and so on. So our compiler achieves this using a set of heuristics adapted from prior work, and you can find details about that in the paper. So the output of the compiler is basically an executable which has these primitive QCCD operations like splits, merges, and so on. In terms of coming to the simulator, we again face a difficulty that current simulators don't really work well for this problem. So simulators like Qiskit Air actually simulate the algorithm's output, and they don't really simulate QCCD devices. And this kind of simulation method actually does not scale beyond 50 to 60 qubits also. So to study systems with 50 to 100 qubits, we built a custom device simulator, which actually does not look at the algorithm's full exponential output state vector, but just tries to estimate the performance and fidelity of the application, not the exact output. So to do this, we have a set of execution time models and a set of gate fidelity models. And all of these models come from prior works on real system characterizations. So to quickly go over the operation time models, we consider 4 different gate implementations based on the different laser parameters that I mentioned earlier. For each of these implementations, the works shown here give us the corresponding gate durations. Similarly, for shuttling, this work shown here tells us the time required to perform these different operations, which has been measured on real experiments. So to simulate, simulating fidelity is one of our key objectives with this paper. So we model the gate fidelity as a factor that depends on the background heating rate of the trap, the gate duration, the chain's heating rate, and instabilities from the laser beam that is used to perform the 2-qubit gate. So the overall 2-qubit gate fidelity model that we use is based on known physics for these kind of systems. So the fidelity depends on, the fidelity term has fidelity equation has basically two terms. The first term depends on the gate duration and the background heating, and the second term includes the factors from just the chain heating and the laser beam instabilities. So what this model tries to describe is that if a gate takes a long duration to finish, the fidelity is going to be bad. And similarly, if the ion chain in which the gate is being performed has been heated up because of a lot of shuttling, the gate is again going to have infidelity. Now, this gives us the fidelity for one gate. So to compute the fidelity for the overall program, we basically take the product of the individual gate fidelities. And this model also has been shown to work well in practice in these studies. So coming to experimental setup and results, we used 6 NSQ applications with up to 4,000 gates. We considered trap capacities with 15 to 35 ions in each trap. We look at 2 topologies, one of which is Honeywell's current topology. We look at 4 different 2-qubit gate implementations, which are the most common gate implementations, which are used in real experiments. And we look at 2 methods of chain reordering. So here I show the results from studying the impact of trap sizing. So for this study, we consider a device having Honeywell's topology, a linear topology with 6 trapping zones, and we consider these frequency modulated 2-qubit gates. So in the first figure on the left, we have the trap capacity on the x-axis and the time on the y-axis. So higher time is worse performance. So you can see that as trap capacity increases, for almost all the benchmarks, the performance becomes worse. There are some applications like square root, which are relatively independent of the trap capacity. That is, their performance does not worsen monotonically with increasing capacity. And if you look at one of these cases, for example, QFT, where we look at the split up of compute and communication time, we can see that in this application, communication time, we can see that the compute time is what dominates the overall execution time, and it increases linearly with increasing trap capacity. So this is because the gate time in larger traps is much higher. So although prior works have conjectured that the performance of QCCD systems is likely to be bottlenecked by shuttling time, our work shows that performance can actually depend very much on application characteristics and on the architectural choices. And we see that small trap sizes like 15 to 25 ions work well and give good performance. Now, doing a similar study for the fidelity, now we have the fidelity on the y-axis, and higher fidelity is better. So we see that there are some applications where the trap capacity doesn't matter. We have high fidelity irrespective of what capacity we choose. But the general trend we see is that the fidelity is low at small capacities, and it is also low at very high capacities. So this happens because at low capacities, you have high communication, which leads to more shuttling, and that leads to worse gates. With high capacity, there is less communication, and the average heating in the trap reduces. But we found that the heating effects are actually spread across large chains. So there is it's as if there's a huge it's as if there's a large hotspot in the device, and because of this, many gates become error prone, and this worsens the overall application fidelity. So there is a sweet spot of about 15 to 20 or 25 ions, where applications tend to have good fidelity. So the key design insights from our work are that first, in terms of trap sizing, as I mentioned, there is a sweet spot of 15 to 25 ions. That depends on the application, which works well and gives us both good performance and good fidelity. And this trap size minimizes the heating, it minimizes the presence of the hotspots and laser beam instabilities. In terms of communication topologies, we found that the topology depends on the communication requirements of the application. So grid topologies work well for communication intensive applications. And we found that if we optimize our trap sizing and topology, we can potentially improve the fidelity of our applications by about 3 orders of magnitude. Similarly, for gate implementations, we found that the application characteristics matter a lot. We found that the frequency modulated and phase modulated gates work well for communication intensive applications, and the amplitude modulated gates work well for nearest neighbor applications. So this tells us that the microarchitecture in these systems must be reconfigurable to really achieve very good reliability. And we found that these gate choices are very important in that they can influence the fidelity by one more order of magnitude. And finally, we found that swapping, the shuttling implementation is also very important, with this gate-based shuttling implementation being much better than physical ion swapping. You can find details about this in the paper. So to conclude, current trapline systems are based on the single trap architecture, which does not scale very well. And QCCD is one of the leading paths towards larger systems. In fact, the first system was very recently developed at Honeywell. And we've developed a design tool flow for the next major milestone of 50 to 100 qubits. And using noise models from prior real system studies, we have evaluated important architectural and microarchitectural attributes in these systems. And we show that there's potentially 4 orders of magnitude improvements that we can make in reliability if we co-design our hardware and software. Thank you.